which test is better, root test or ratio test? So the short answer is that root test is better. So what I mean by that is that if some series, of course, require to be positive series, where every term in the series is positive. So if a series is, so we all know that both root test and ratio test, they are not universal tests, because if the series converges very slowly, then both of them may fail. So root test can test more series than ratio test, can succeed in more series than ratio test. So we're going to first prove this inequality. Lim inf of an plus 1 over an is less than or equal to lim inf of the nth root of an is less than or equal to lim sup of nth root of an. So this part is obvious. We're going to prove the right-hand side. So the left-hand side can be proven using the same steps. So this part is less than or equal to lim sup of an plus 1 over an. So this part is not obvious. So I'm going to prove the right-hand side part. So the left-hand side part, I'm just going to skip it. For the same reason, it can be proven. So right-hand side, the reason is because if we set lim sup of an plus 1 over an to L, perhaps, right? Then remember, of course, every term is positive, right? So that the lim sup is also positive. I think so. Also positive. So that here's again my claim that so for any epsilon that's positive, right? Here we have L plus epsilon, right? To the right hand side of L plus epsilon, we only have at most finitely many members of Bn denoting an plus 1 over an, right, as a whole entity, as a sequence, right, at most finitely many. Why? Because if otherwise, if to the right-hand side of this point, if we still have infinitely many of them, of members of Bn, we would still be able to find a convergent subsequence, right? Who has the limit point of value of greater than or equal to this point, right? So meaning we've somehow found another limit point that is bigger than this limit point, but this limit point is given to be lim sup, meaning it is the biggest limit point out of all the limit points, where each limit point is a limit of a subsequence. So our claim is really correct. So in other words, there exists capital N where as long as small n is bigger than or equal to capital N, we always have infinitely many members to the left-hand side of this point. Right? That's the equivalent statement to this statement. So we have, after this term, we have an plus 1 over an is always to the left-hand side of this point, is always smaller than L plus epsilon for any value of positive epsilon. Right now, I just fix epsilon. Later, I'm going to let epsilon approach 0. Right now, just fix it. Now, according to this logic, right, it says after a certain fixed capital N, right? So we say A sub capital N plus 1 over A sub capital N is less than L plus epsilon. And next is A big N plus 2 over A big N plus 1 less than L plus epsilon, so on and so forth. A sub small n over A sub small n minus 1 is less than L plus epsilon. Right now, I just fix small n, right? Multiply everything together. So right now I have A n plus 1 over A n multiplied by A n plus 2 over A n plus 1, so on and so forth. A small n over A small n minus 1. So that is equal to this one cancel out, right? This one cancel out with the next one, and the last one cancel out with the previous top one, right? So in the end, I have A small n over A big N, still less than multiply everything together on the right hand side. So L plus epsilon to the power of how many times? So here's n, big N plus 1. I think it's small n minus big N. This many times. Right now, remember, big N is fixed. We're going to let small n approach infinity. So now, which means A small n is smaller than A big N times L plus epsilon to the power of small n minus big N. Right now, we take the nth root on both sides. Right? Everything is positive, right? Yeah, given positive series. So nth root of an is smaller than the nth root of, I'm going to combine A big N and L plus epsilon to the power of big N. Right, since the power is minus big N, therefore I just put it on the bottom. Right, so combine these two. So I'm still left with L plus epsilon quantity to the power of small n. Right, I haven't used this term yet. But then I have to, like I said, take the nth root. Right, take nth root to this power. So this power is gone. So L plus epsilon. So we're going to this time let n approach infinity and take the lim sup, because I don't know if there is a limit of an, but there's definitely a lim sup. Right? Lim sup. But the nth root of an is a sequence. Lim sup definitely exists. Smaller than or equal to this lim sup, but this already has a limit already. L plus epsilon is a constant. We fix epsilon, right? And capital N is also fixed. So therefore, inside here we have a fixed positive constant, and we take the nth root. So that's a well-known limit. That's approaching 1. So that is L plus epsilon. Right? So left-hand side, lim sup is already a constant. That's after we take the lim sup, right? So this already becomes a constant. So since this inequality is always true for any value of positive epsilon, right? Always true, right? So therefore, it must be also true if we let epsilon approach 0. Right? This is not cheating. Right? First, we held epsilon fixed, right? Then we take lim sup. Then we let epsilon approach 0. That's totally legal. Right, totally legal. So this time, lim sup, right, as a constant is smaller than or equal to L, right? Epsilon gone, right? Approaching. So L is lim sup of an plus 1 over an, right? So really, this is really true. So I'm just going to skip the left-hand side, right? The left-hand side, using the same logic, Now coming back to the very first problem, that here's why root test is in some sense better than ratio test. Because using this proven result, right? If let's say ratio test succeeds, in other words, if somehow we've shown that the lim sup of the ratio, right, this ratio is strictly less than 1, then using our result, lim sup of the root is already no larger than lim sup of the ratio. Right? And we've shown the lim sup of the ratio is strictly less than 1. So which means the lim sup of the root is also strictly less than 1. Using our Cauchy root test, right? If the lim sup of the ratio is strictly less than 1, then it's convergent, right? Meaning root test also succeeds, right? In other words, if the ratio test succeeds, root test also succeeds. If otherwise, if the let's say if the ratio test fails, right? Then how about the root test? Can the root test succeed? Right? Previously, we've shown that if the ratio test succeeds, then the root test definitely succeeds. Now, if the ratio test fails, right? Root test, I say, may still succeed or fail. Sometimes may still succeed, right? May or may not, may succeed. Depends. Here's an example. So we have a series. Say 1/2 plus 1/3 plus 1/2 square plus 1/3 square plus 1/2/3 and 3/4 No, 2/3 power increase power 1 2 power 3. Then same base 3 power this time increased to 3. So here's the pattern, right? So for the all terms, right, we have 2, right? At the bottom we have 2 to the power of 1, 2, 3. Even terms we have 3 at the bottom. Power is 1, 2, 3 all the way. Right? So perhaps generally speaking, we have, if it's even term, we say a 2n can be expressed as 1/3 to the, let's say, if n was 1, we have a2 is this one, power is 1. If we have n is 2, we have a4 is this one, power is 2. So it's 3 to the power of n, right? Depending on the value. If we have the a6, right, 6 term, 1, 2, 3, 4, 5, 6, we have power of 3, right? 3, 2 times 3, right? Exactly 3. So we have even all terms, 2n minus 1. What is that? A base of 2. So first odd term is power is 1. Second odd term, power is 2. So I think it's n, right? If it's n is 1, we have first odd term, right? It's power of 1. Second odd term, n is equal to 2. We have a3. a3 is this one. Power is 2, right? Really. So can we use ratio test, right? Can the ratio test succeed or fail? Let's find out. So ratio test. So I'm going to use, like I said, this time our general term does not have a limit, right? Because we have two subsequences having different. They have the same limit, but once we take the ratio, they have different limits, right? Once we take the ratio, for example, if the ratio was a2n over a2n minus 1, if this is the ratio, right? What's this? What's this limit? Okay. That is equal to 3 times 2 to the power of n, right? Does this have a limit, right? 2 over 3 to the power of n, right? As n goes to infinity. It's tending towards 0. Right? So if we have another possibility, if we have, let's say if it's if it's 2n plus 1, right? Previous we have even term over odd term. Now we have odd term over even term. Right, let's say, perhaps let's use 2n. Right, what's going to happen? 1 over 2 to the power of, this time we have, here's n, replace n with n plus 1. Well, n plus 1, right, times 8. So 3 to the power of n, that is 3 over 2 to the power of n, and still have 1 over 2. Right, the constant. But this time n goes to infinity. It's going to approach positive infinity. Right. So indeed, this time the ratio as a sequence, right, does not have a limit because we have two subsequences that have different limits. One limit is 0, the other limit is positive infinity. If we consider it as a generalized limit. So which means if the lim sup is less than 1, but this time lim sup is positive infinity, it's not less than 1. So we cannot tell if it's convergent, right? So definitely not convergent. But if it's lim inf is bigger than 1, it's divergent. Right? Can we show lim inf is bigger than 1? No. Lim inf is 0, it's not bigger than 1. So there's no way we can tell if it's divergent. Right? We cannot be sure. Right? It only says, it's only a sufficient condition. Right? If it's less than 1, we can say it's convergent. But if it's otherwise, we cannot say it's definitely not convergent. Right? There's no, we cannot be sure of that. Right? We cannot be sure of whether it's not divergent for sure. Right? So it cannot be determined. So in this case, I think the ratio test kind of fails. So the ratio test failed. So let me use the root test. Right? It may succeed or not. Let's find out. So using the nth root of, first let's use this one. The nth root, but this time I'm using 2n. So the 2nth root of a2n. That is the 1 over 3 to the power of n, then to the power of 1 over 2n. Right? That is 1 over square root of 3. And using odd term, right? The 2n minus 1th root of a2n minus 1. That is the 1 over 2 to the power of n, then over 2n minus 1. That's what it means. Right? as n approaches infinity. As n approaches infinity. So this, of course, go on forever. As n approaches infinity, this is going to tend toward. Power is going to tend toward, I think it's half. So square root of 2. Right? So looks like we have, looks like this limit, this sequence doesn't have a limit because it has two subsequences that have different limits. Right? But we only have two different limit points, right? So the biggest limit point is what? Is this one, right? That's the lim sup, meaning the biggest limit point. Right? Right, so really, lim sup is it less than 1? Yes, it's less than 1. Then it's convergent. Right? So root test succeeds this time. It may not always succeed. But so in this sense, I say root test is better than ratio test. But sometimes ratio test can be more convenient than root test in some certain problems, such as series that involve factorial. Like if we have general term that involves factorial instead of power of n, maybe we use ratio test will be more convenient. Right? If the general term contains power of n, then we may use root test just to cancel out the power. Right? Then that may be more convenient. But in this sense, right, in terms of the width of applications, right? So this is what I mean. The root test is better because every time the ratio test succeeds, the root test definitely succeeds. If the right in terms of convergence, if it's divergence, if the ratio test succeeds, then the root test definitely succeeds. Right. So the root test, in this sense, has a wider application. But both root test and ratio test are not very good tests because if we have a series that converges very fast, that converges very slow, then both of them may fail. In next video, I will prove that, for example, root test or ratio test, they can only succeed in testing series that converges very fast, such as geometric series. Q, for example, absolute value is less than 1. Right, Q to the power of n. If the series converges slower than this geometric series, then they both fail.